Hello everyone, this is the accompanying media submission for the ICRA 2026 paper titled Clutter Nav, Gradient Guided Search for Efficient 3D Clutter Removal with Learn Cost Maps. The objective of this work is to address efficient clutter removal and robotic manipulation, focusing on two critical goals: minimizing structural disturbance to a given clutter and retrieving a specified target object with as few removals as possible. Existing approaches either rely on rigid heuristics or require extensive computation, often failing to generalize to dense real-world clutter. Our work aims to bridge this gap by learning a decision-making policy that balances both objectives in a unified framework. Our approach overcomes the limitations by introducing a learned removability score estimator. This estimator is trained in simulation using reinforcement learning from episodic demonstrations. The core of our method is a lightweight 3-layer MLP that predicts the removability cost for each object based on spatial and geometric features which are extracted from the observable point cloud for that object. To incorporate target retrieval, we augment the removability scores with gradient-based evaluation techniques. In our framework, the environment consists of approximately 30 objects during training. The action space is defined as a selection of an object to remove. The reward function penalizes both the number of removals and the total disturbance caused. We utilize a critic-centric soft actor critic architecture where the critic outputs object-wise removability scores. To prioritize objects that facilitate target retrieval, we compute gradient-based importance scores. Specifically, we use integrated gradient to quantify how the presence or removal of each object affects the removability cost of the target. This approach enables counterfactual reasoning to identify which objects, if removed, would mostly improve the target's accessibility. The final importance score combines normalized removability cost and gradient magnitudes. We evaluate our approach across diverse clutter scenarios, random clutter, stack structures, structure resembling walls, and pyramidal formations, and also across different objects from the YCB dataset. We compare the performance against different baselines such as a random policy, a conservative cost-driven policy, and a goal condition RL baseline. Our method consistently achieves lower disturbance and fewer removals to reach the target. We see promising results with the YCB objects showing that the feature extraction can generalize well to unseen and complex geometries. We create a fully automated and autonomous pipeline in PyBullet using perception to extract features, using the algorithm to select next object to be picked, and using standard motion planning to facilitate the pick and place in simulation. We validate our approach in real-world settings by combining actions given by the algorithm with waypoint navigation, where waypoints are given manually for the action object to facilitate pick and place. We are focusing on creating an end-to-end code base to serve as an easy deployable setup on different hardwares with ROS middleware. Upon analyzing a decision trajectory from the algorithm, we see how the gradient prefers objects close to the target, which are either above or to the side, blocking it as shown by the high gradient measures, and the high removability cost at the periphery shows the safety considerations. Overall, the combined score shows almost human-like behavior, uncovering the clutter one layer at a time. Thank you.